Okay, so it's really the end. So the last thing we want to do is to connect linear programming and nonlinear programming in the way of duality. Okay, so duality is used both in LP and Lagrange duality. So obviously there must be some similarity. We have already mentioned a lot of their similarities. They both have weak duality, strong duality, complementary slackness. And also, we both have the one-to-one correspondence between primal constraints and dual variables. So now we're going to give you one last fact. LP duality is actually a special case of Lagrange duality. So this may not be so useful if you want to solve problems, but this again help us get a chance to appreciate the beauty of mathematics and operations research. Okay, so we're going to take a primal LP and try to apply Lagrange duality on it, and then show you that its Lagrangian dual, it'll be indeed the dual LP. Okay, so that's our plan, and let's try to do it. Let's consider a primal linear program. Okay, we want to maximize C transpose X subject to AX equals B and X non-negative. So once we have this, then if we want to apply Lagrange relaxation, Lagrange multiplier on it, then for each constraint here, we are going to say you have a lambda value. So we're going to give m lambda into this program. So typically we say A is a matrix and A has the dimension which is m times n, okay? You have n variables and m constraints in your primal linear program. So that's why here you associate m lambda. One thing that is interesting is that here we will keep x non-negative in your primal program. We only relax the equality constraints. You may want to ask why, and very quickly you will see how that is how that help us do the proof. Okay, so once we do that, we're going to get our Lagrange relaxation, which is this one. We simply put the equality constraint to our objective function. Here again, several things. So first, you are trying to solve this Lagrange dual problem. So you need to first find your optimal x. But your lambda transpose B has nothing to do with your x, so it can be taken outside of this maximization problem. Also here, your lambda actually has no sign constraint on it. Why is that? Because there is no multiplier with a specific sign that may always reward feasibility for equality constraints. What does that mean? In the past, if you say AX is less than or equal to B, then whenever we have B minus AX, we know if X is feasible, this must be non-negative. But here, this is equality. Then in that case, you really have no idea whether your lambda should be positive or negative to reward feasibility, because either way is possible. Whenever X is infeasible, it may be positive or negative. All right? So how should we do? Then in that case, our lambda would be unrestricted in sign. Okay? And we will let the optimization to determine whether lambda should be positive or negative. All right? So now our Lagrange dual program is the following. We want to find the lambda, which can be any sign. We want to find lambda to minimize this particular function, or this should be ZL, ZL of lambda. And the ZL of lambda, as we mentioned, is this one. So now the Lagrange dual program is to search for lambda that minimizes this ZL of lambda, all right? And this ZL of lambda requires us to solve a maximization problem. Okay, so now is the interesting part. Our dual program here is meaningful only if your C transpose is less than or equal to lambda transpose A. only if this guy satisfies this. Why is that? Well, let's take a look at this particular maximization problem. Suppose you may find any xi that makes C transpose I greater than lambda transpose AI. So this looks a little bit weird, so let's make it slowly. This particular thing, in some sense, is a vector multiplication, or you may call it an inner product, okay? So this C transpose is a vector. Lambda transpose A is another vector. So you may say you want to maximize the sum of all these particular cases. You have n variables, okay? So for this particular vector, you have its ith element multiplied by the xi. Okay, so this is actually that. So if you are able to find any I such that this particular number is positive, then what's going to happen? If you have a positive term here, then for your non-negative x, you're going to push your xi to be infinity, and then your problem becomes unbounded, all right? So if that would be possible, then there is no way for you to do your minimization. Your lambda, the choice of lambda must be smart such that this particular inequality is true. You need to choose your lambda such that the whole thing here, all its elements are not positive. It must be 0 or negative. Or you may say your C transpose must be less than or equal to lambda transpose A. Only if that's true, then your optimization here makes sense. Because once this is not true, the inner part gets to infinity. There's no way to do minimization, okay? So you must make this hold, and then the thing here does not go to infinity. That's the idea. But what's interesting is that once you choose lambda to make this happen, then this maximization, the best thing to do is to set all your x to be 0. Why is that? Because if all the terms here are negative, for example, then why don't you just set your x to be 0? And once that happens, this term gets away. So your Lagrange dual program is actually this one. Your lambda can be in any sign, but it must satisfy the only constraint saying that your lambda transpose A should be greater than or equal to C transpose. Then you want to minimize lambda transpose B. Well, that's exactly the dual linear program of your original primal problem. Let's take a look. Originally, this is a maximization problem, so your linear dual will be minimization. That's fine. Also, your C transpose gets to the constraint side. Your B gets to your objective side. That also makes sense. And then it's the sign for dual constraints and dual variables. These are these are primal functional constraints, and they correspond to unrestricted in sign lambda. Why is that? Because if your primal constraints are equalities, your dual variables should be unrestricted in size, right? According to linear programming duality. Lastly, when this is a maximization problem with non-negative variables, then your dual constraints should be greater than or equal to. All right. So all of this altogether shows that, well, the dual program is indeed resulted from the primal program. If you apply LP duality, or if you apply Lagrange duality, in either way, you get the same thing. So that's why we say LP duality is a special case of Lagrange duality. All right? Lagrange duality may be applied to nonlinear programs, but when it is applied to linear programs, it gives you exactly your linear programming duality. Amazing, right? Okay, so that's pretty much the end for today's lecture. Today's lecture may not be so required when you want to solve a nonlinear program because you always have program solvers algorithms, but nice algorithms always depends on nice theories. That's why we really want to give you one lecture to talk about the KKT condition, Lagrange duality, and how they have some nice properties. You may, in the future, in advanced courses, to apply them to better design your algorithms, or at least in this stage, you may appreciate the beauty of mathematics. Okay, that's all I have for today. Thank you.